Start. Okay, perfect.
Has started.
Yeah, perfect. Yeah.
Okay. So reading, I think next one. Can you scroll a little bit? And yeah, I think I want to read this disclaimer. All of the following lessons are Cassandra version agnostic and try to explore the general design and architectural layout of different Cassandra components and operations. Okay. Cassandra use case. By default, Cassandra is not a strongly consistent database. It is eventually consistent. Hence, any application where consistency is not a concern can utilize Cassandra. Though Cassandra can support strong consistency, it comes with a performance impact. Cassandra is optimized for high throughput and faster writes and can be used for collecting big data for performing real-time analysis. Here are some of its top use cases. Storing key value data with high availability. Can you scroll? Yeah. So Reddit and Dig use Cassandra as a persistent store for their data. Cassandra's ability to scale linearly without any downtime makes it very suitable for their growth needs. Time series data model. Due to its data model and log structured storage engine, Cassandra benefits from high performance write operations. This also makes Cassandra well suited for storing and analyzing sequentially captured metrics, that is, measurements from sensors, application logs, etc. Such usage take advantage of the fact that columns in a row are determined by application, not a predefined schema. Each row in a table can contain a different number of columns and there is no requirement for the column names to match. Okay.
Yeah.
Uh,
So this is on contrary to the SQL databases that we have, right? Like each row in the table can contain a different number of columns. There is no requirement for the column names to match. So basically, consider one row to have, let's say, 5 columns. Another row can have 10 columns too. So that's why actually they are generally called as columnar database too.
yeah. Okay. So write heavy applications. Cassandra is especially suited for write intensive applications such as time series, streaming services, sensor logs, and Internet of Things application. Okay, so high level architecture. This lesson gives a brief overview of Cassandra's architecture. In that, I think data partitioning, Cassandra keys, clustering keys, partitioner, and coordinator nodes, I think, are the main components. So let's start with Cassandra common terms. Before digging deep into Cassandra's architecture, let's first go through some of its common terms. Column. A column is a key value pair that is the most basic unit of data structure. So column key, which is uniquely identifies a column in a row. Column value stores one value or a collection of values. A row is a container for columns referenced by primary key. Cassandra does not store a column that has null value. This saves a lot of space. So the Cassandra row here, which is a container. Can you scroll a little bit, Anne, to the diagram? Yeah. So this is a row container for columns referenced by primary key. So row key is a primary key, and in that we have multiple columns basically, and it does not basically have null values. So one row can have multiple columns, right? It does not need to be the same set of same number of columns. For example, one this row key can have 5 columns, and the in same row can we have like 3 columns again? Is that possible?
No, same row can't have it, right?
Oh,
Because
sorry,
the
another row.
primary key
My bad. Another row
will be
can have.
unique.
So one row can have 4 columns, a second row can have 3 columns, a third row can have 2 columns, so on and so forth, right?
Yeah.
Different number of columns.
Think it's key value like how the map stores in
So row key and then column keys and then the value, something like that it is.
Yeah, but all the number of columns is not consistent throughout. That's what
Yeah, that's
it's.
what in the map also it's not consistent, right? In the map too, you can
Yeah.
put any number of like
Yeah,
again maps, something like
Right.
that.
Right.
yeah. So a table is container of rows. Key space is a container for tables that span over one or more Cassandra nodes. Okay. The cluster containers of key spaces is called a cluster. Node refers to computer system running an instance of Cassandra. A node can be physical host, a machine instance in the cloud, or even a Docker container. Cassandra is a NoSQL database, which means we cannot have joins between tables. There are no foreign keys, and while querying, we cannot add any column in the where clause other than primary key. These constraints should be kept in the mind before deciding to use Cassandra. I think yeah, this is pretty straightforward. Going ahead with the high level architecture, data partitioning. Cassandra uses consistent hashing for data partitioning. Please take a look at Dynamo's data partitioning. All consistent hashing details described in it applies to Cassandra too. Okay.
Yeah, can we scroll up a bit? Yeah, so when we are talking about the topology, like so everything is part of a cluster here in Cassandra. It's never a single instance that we think of. Like let's say whenever we are trying to read or write, it always takes place through a cluster. So cluster, that means there could be set of hosts storing the data, and if it's a cluster, that means there will be multiple node. That means the key space as in the record of all the rows. That key space is distributed across multiple nodes. That means, let's say if we have 100 records, then our key space size is 100. And let's say our cluster has four nodes or four instances where Cassandra is deployed, then those 100 rows would be distributed across those four instances. And when I say distributed, those would be replicated too. It's not that 1 to 25 will be on first node, 25 to 50 on second, and like that. Even though there could be a primary copies uh, of this 100 record key space in multiple hosts, but it will also have a copy. Like there will be a main copy and then there will be a replica copy, right? So 1 to 25, if we put it on the first node, then we might put its replica copy on third node or like that. So that's how it's distributed across multiple instances with the copies. And when it comes to consistent hashing, um, consistent hashing is the main point of contact where any query will come. It will look up into consistent hashing and it will try to find the nearest host where that key could be located. Either the primary copy or the replica copy could be located. So any read request comes, it can go to any of the copies, and then it could serve that read request. Same happens with the write. It will first try to find where could this record be inserted, and it will just write it, and then the replication will take an effect in the background. So that's on a high level, like in a very crude manner, that's how read write takes place. um, Something similar to what we were doing in distributed message queue. Whenever a message is published, we try to copy it in the other one. So just try to relate to the basics, in terms of replication, in terms of like the number of copies we need, and the cluster part. But yeah, there will be specifics to here. So I'm just trying to like put some blocks, like high level blocks, or components, and then as we go forward we will see what each component signifies. So the cluster will be like all nodes together. If you scroll down, can you scroll down, Annie? Yeah, yeah. So it says for data partitioning. So like I was talking about 1 to 25, 25 to 50, and all those basically partitions, right? So we use consistent hashing through that. So um, like that's where like basically the queries will be routed, and through that we will basically fetching the instance, and then we'll be routing the request to a particular instance. So and then that would be like wherever the request goes, that particular node will start acting as a coordinator here, without any other without having the primary and secondary. Wherever the request goes, that will start as as a coordinator, and then it will try to coordinate that particular write request or a read request in terms of committing, in terms of reading the data or matching the data, or the consistency levels. So just wanted to like put the building blocks or the components here so that we can try to relate further.
Yeah. So, Cassandra keys. Shall I read ahead, or anybody has any questions?
Yeah, yeah, feel free to interrupt and ask questions if any in the about thing. If you can scroll up like these notes and anything, if there is any question, feel free to go ahead. Like,
Yeah. So I think, yeah, let's look at the mechanisms that Cassandra applies to uniquely identify rows. So first is Cassandra keys. The primary key uniquely identifies each row of a table. In Cassandra, primary key has two parts. So primary key is equals to partition key plus clustering key. So a partition key decides how data is distributed across nodes, and clustering key decides how data is stored within a node. Uh, okay, the partition key decides which node stores the data, and the clustering key decides how the data is stored within a node. Let's take
yeah,
the
so the first one I was talking about, right? Like first one is like where to route the query, where to route the particular request, and then into that particular node wherever the request has the partition is, we are trying to find the exact record. So that's the partition key and a prime and a clustering key.
So I just want to understand how this clustering key decides how the data is stored within a node. I think I'm clear with partition keys, um, but the clustering key decides how the
So
data is stored within.
consider it this way. Let's say we are storing data A to Z, like names. Like let's say we have a employee data, and we have employee names starting from A to Z, and let's say we have four nodes here. So for four nodes, let's say how many partition we can create out of 26 characters. Let's say if out of 26 characters, we can create four nodes, as in there could be six character initials. Like let's say, for example, all the records from A to E could be kept in node 1. All the records from, let's say, F to L could be, or F to M could be kept in another one, and likewise basically. Let's say if we partition it into four nodes, then the partition key will define whether it's first node, second node, third node, or fourth node, whereas the clustering key will tell uh, whether it is A, B, C, D, or E. So, or within itself, there could be A B, A C, and like sort of a sorted order of the record, right? So once we to reach the node where the exact let's say if you are trying to find something like Sagar. So for Sagar, it will basically probably send us to fourth partition. So our partition key will be set in such a way that it would point to the fourth partition. And in partition key itself, let's say the fourth partition starts from R to Z. So in that, the clustering key could be 2. So R will be the first name, and anything starting from S will be the second name. So in that node itself, we are trying to find the record, which is the second record. So our clustering key could be 2. Does it make sense?
Yeah.
So clustering key is basically nothing but trying to sort it as per the first. So let's say we try to split the data by taking this example here. Let's say we try to split the data based on city and employee ID. So let's say for a state-wide data, all the cities we will have both of the fields, right? So all the employees from, let's say, San Jose would be stored on the same node. And on that same node itself, if we want to find a specific employee, then we will need a clustering key. So with the partition key, we'll be able to reach out to the node which stores all the data from San Jose, and then in that particular node, we'll try to find the exact employee. So that's where our clustering key will help
Okay.
to find unique record. Let's say there could be Sagar in San Jose, and there could be Sagar in New York, and there could be Sagar in, let's say, Seattle. So just giving the clustering key won't help to locate a unique record, but the Saga but Sagar who stays in San Jose might give us a unique record. That's the basically idea here.
Okay.
Sagar, can clustering key be same like in all partition? Is it possible?
Sorry.
Uh, like, uh, can clustering key be same in different partitions?
So yeah, definitely, right. Let's say, as I mentioned, like one partition is, let's say, San Jose, and another partition is New York. So there can be Sagar in San Jose, and there can be Sagar in New York, right?
Okay.
Okay.
So
So,
the Sagar in San Jose combination is unique here, not Sagar in itself.
okay.
Does
So,
that answers your doubt, Tejasvi?
Yes.
So basically, we are just trying to categorize the records in such a way that that will help us break it down. Yeah. So if you see, it's just simply a logical way of breaking down the data, like this partition key clustering key thing.
should I go ahead with the reading if anybody does not have any question? Okay. Um, so the partition key decides which node stores the data, and the clustering key decides how the data is stored within a node. Let's take the example of table with primary key, city ID and employee ID. This primary key has two parts presented by two columns. City ID is the partition key. This means that data will be partitioned by city ID field. That is, all the rows with the same city ID will reside on the same node. Employee ID is the clustering key. This means that within each node, the data is stored in sorted order according to the employee ID column. Can you scroll? Yeah. So, as described above, clustering keys define how the data is stored within a node. We can have multiple clustering keys. All columns listed after the partition keys are called clustering columns. Clustering columns specify the order that the data is arranged on a node. So partition key is, say for example, state, and the clustering key can have city and zip. On a node, data is ordered by the clustering key. Okay, yeah, that actually clears now. So other state is say WA, in that we have cities and the different zips. So clustering keys, we actually tell what how we want the data to be stored. Okay, yeah, you can scroll a little more or partitioner. If anybody wants to read this one, I'm not okay with it. Okay to shuffle.
Does anyone want to read? Or
I can read.
okay.
Partitioner is the component responsible for determining how data is distributed on the consistent hashing ring. When Cassandra inserts some data into a cluster, the partitioner performs the first step, which is to apply a hashing algorithm to the partition key. The output of this hashing algorithm determines within which range the data lies, and hence on which node the data will be stored. So here we have the keys, the table with the keys, and then it goes to partitioner, gets applied the hash function, and it's get divided into different partition. By default, Cassandra uses the murmur3 hashing function. This hashing function will always produce the same hash for a given partition key. This means that we can always find the node where a specific row is stored. Cassandra does allow custom hashing functions. However, once a cluster is initialized with a particular partitioner, it cannot be changed later. In Cassandra's default configuration, a token is a 64-bit integer. This gives us a possible range for tokens from -2 raised to 63 to 2 raised to 63 minus 1. All Cassandra nodes learn about the token assignment of other nodes through gossip. This means any node can handle a request for any other node's range. The node receiving the request is called the coordinator, and any node can act in this role. If a key does not belong to the coordinator's range, it forward it forwards the request to the replicas responsible for that range. Coordinator node. A client may connect to any node in the cluster to initiate a read or write query. This node is known as the coordinator node. The coordinator
Yeah, so
identifies.
I think this is something which I was earlier talking about. Like, client may connect to any node in the cluster to initiate a read or write. So, like we are talking about uh, like scalability, right, or availability, right? So, how our system could be highly available or highly scalable is, let's say if we have four node, or let's say six nodes. Now any node can basically accept the read request. So that basically parallelizes or horizontally scales the number of requests we can accept at a given moment. Compare this with the master slave, where only master can accept any so at least let's talk about write request only. So the write request only goes to the master. So master can only hold up to certain number of connections. So the availability is limited to number of connection that master can hold. Here any of the six nodes can um, can start the read write operation. So they will be able to hold like 6 times more connections at a time. So that tells us basically the availability is more here. So like this is where basically the main difference comes in. So if you see, like the request will be served or served by the coordinator node, but if the coordinator doesn't have the data, it will get the data from the respective nodes. But the request itself will be served by the coordinator node.
Should I go down?
Does that clear? Is that clear? Like to everyone? Like this is the basically this is the main difference.
Sandra, are we supposed to know the mechanism picked by client to pick the coordinator node in the beginning or no?
Can you come again?
So, are we supposed to know from client any random node can be a coordinator node, right? As in, for example, client can choose any node for read and write request, right?
Yeah.
How does that happen? I mean, what mechanism client uses to pick a random node or particular node?
So it will, let's say it will just go to the consistent hashing ring, and it will just point us to any particular record, let's say. And that way it will just be able to actually go to the any. So we had the clustering key, right?
Yeah.
Sorry, we had the partition key, right? So through partition key, it will just try to connect with any of the nodes, and then it will be able to basically serve the request.
Okay.
There will be another component in front of these nodes which will basically route the request. uh, it could route to any of the nodes, or it could route to specific node too.
Okay.
Should I go down?
Yeah.
Uh,
Any other doubts? Okay, let's go.
So now if
replication. So we'll be covering replication factors strategies. Each node in Cassandra serves as a replica for a different range of data. Cassandra stores multiple copies of data and spread them across various replicas so that if one node is down, other replicas can respond to queries for that range of data. This process of replicating the data onto different nodes depends upon two factors: replication factor, replication strategy. Replication factor decides how many replicas the system will have. Replication strategy decides which node will be responsible for the replicas. The replication factor is the
uh,
number of nodes.
Sorry to interrupt, Tejasvi. Asha, I think, can we scroll up even more? Asha, here, like your question was like, where would the client, how would the client know where to go, or which node to go for the first time, right?
Yeah.
Yeah, okay. So sorry, my bad. Like I think I was thinking about something else. So the client can basically connect to any node, any random node. It doesn't matter which node it is. Like any node closest to it, it can just simply connect to it. Uh,
Okay.
yeah. And then whenever, if the client connects to, let's say, server one, the let's say the one which is pointed as a coordinator node here, if that node doesn't have the data, then it will look up into the consistent hashing ring, and then it will get the exact partition or exact node where the data could be, and then in the background it will try to get that data.
Okay.
Yeah.
Makes
So
sense.
yeah. So first point of contact could be any node. Whichever node the client reaches out to first starts acting as a coordinator node.
Okay.
Can you scroll a little bit up? It's here somewhere, like little bit, like in between. So
Sorry.
here it says the node receiving the request is called. Can you scroll a little bit down? The node receiving the request is called the coordinator, and any node can act as in this role.
Yeah, yeah, yeah.
Yeah,
Correct.
my question was how that any node is identified by the client, but that clears now.
Yeah.
Got
It
it.
could be basically any closest node, or it could be, let's say, consider that there is a proxy service on top of our Cassandra cluster, or let's say there is a load balancer on top of our Cassandra cluster. So the node balancer can distribute the request randomly.
Okay.
So there will be some proxy from where the request will be coming in to answer your specific question, and then these requests can be distributed evenly or like randomly across any node, and whichever node the request first reaches to starts acting as a coordinator node. Now compare this with the SQL one, where the request will always go to one of the masters, and the master uh, will be the partition leader itself. Like, so for any record you're trying to write or read, it will first look up which partition should it go to, and in that partition will have its own cluster, and the request will go to the master of that cluster. So even before identifying master, they will try to resolve like which partition it is, and then in that partition it will just tries to go to the master. Now here it will first the request will first be received by any coordinator, and then it will look up where the data is located, and then it will try to fetch the data in the background. Does it make sense?
Yeah, that's why they say high throughput.
Yes, exactly. Yeah. High throughput is just because like any node can serve the request. So
Yeah.
at a time, all six nodes can should be able to serve any request that is coming in. So that actually increases the throughput. Let's say six requests are coming in for the record located in San Jose only. Let's say. So here all six requests can go to any random node, all six nodes. Whereas in the in the leader follower case, it will go to the same master. So the same master will needs to serve all those requests basically. Is it clear? Uh,
Yeah.
any Asim, I think you were asking something.
No, nothing.
Okay.
I do have to drop, so I'll have to stop the recording. Uh,
Yeah, I think we can stop here. Right? We are already about time. So yeah. Any uh, anyone has any question or